this is basically based on a work with Nathael Gozlan, Shohei Nakamura, and Hiroshi Tsuji. And also, if I have the time, I will mention another related work at the end of the talk. So this is the line. I will start with the motivation for this problem. You already heard about the Blaschke-Santalo inequality. Then I will spend some time in recalling some basic classical results about Gaussian and Gaussian semigroups and log-concavity. Then speak about what happens when you look at the Legendre transform in this context, and then go back to the motivation, which was understanding the evolution of the volume product here. And I hope I will have time to discuss the non-even case too. Okay, so we are working on Rn. I will denote V2n the Euclidean ball. We already saw this notation. Given a convex body, K, I will denote K polar, this set. So it's the set of all hyperplanes tangent to the boundary, the convex hull of this. So this definition is, of course, very much dependent on the choice of the origin. But first note that if you take the operation twice, this is basically the Banach theorem. This tells you that you end up again in K, and the Euclidean ball is a fixed point for this operation. Okay, so as I said, this is sensitive to the origin. So if you have, for instance, a convex body K, and 0 is not inside your convex body, of course you can separate. So you have half space here, and by definition, this whole half space will be in the polar, right? Because it's negative, so negative is smaller than 1. So of course, you have to make some assumptions if you want to end up with again with a convex body. And, it will be a convex body as soon as the origin is in the interior, but we will ask something more. We'll ask that the body is symmetric with respect to the origin. And in this case, you can define the volume product to be the product of the volume of K and the volume of the polar of K. So this quantity is a linear invariant in the sense that if you perform any linear transformation on K, this does not change. So it makes sense to look at, you may ask, what is actually the maximum or the minimum of this quantity over all convex bodies. So I will not talk today about the minimum, but we will look what is the maximum. And the maximum, this famous theorem by Blaschke and Santalo, is that the maximum is attained for the Euclidean ball, and of course for any ellipsoid, because it is linearly invariant. Okay, so I don't know very much about the original proof by Blaschke, which was in R3, if I think. Neither by the one of Santalo, which was more, I think, sketchy, relying on some differential geometry. But somehow the modern proofs emerged in the 80s with a paper of Jean Saint-Raymond, and it was a very nice answer by Meyer and Pajor, who proved that this quantity increases when you do Steiner symmetrization. So if you perform enough Steiner symmetrization, you will end up with the Euclidean ball. This solves the geometric problem. So we're interested in what could be a functional version of this result. And I think we already saw that the functional analog of convex bodies are log-concave functions. So log-concave means exponential minus phi with phi convex. So in this context, what plays the role of the polar is the Legendre transform of your convex function phi, which I define here as the supremum of all x of x dot z minus phi of x. And actually, you can also define the same operation at the level of log-concave function. This is really a matter of state. prefer to work with convex functions, but if you prefer to work with log-concave functions, you can define the polar of a log-concave functions by this formula, which means that you take exactly exponential minus phi star. It's really a matter. I will keep the convex function. So in this context, you can define the volume product, which is the product of the integral of exponential minus phi and the integral of its polar, exponential minus phi star. And you have the same invariance. If you change phi to phi tilde phi of ax, and you can also add a scaling constant, this volume product will not change. And so you can ask again, I should say here, by the same reason as before, I will assume that phi is even, which plays a role of k being symmetric. And you can ask again, what is the maximum or the infimum of this quantity over all even convex functions? And this was observed by this ball that maximum is obtained back for the Gaussian. And note that x squared over 2 here is indeed the fixed point for the Legendre transform. So the proof by Kisball was to use the geometric form, the Santalo inequality, plus some clever use of the level sets. So it's not a direct, I mean, it's just not one line from the geometric, but you can play with the geometric version and some extra observation and get this inequality. And on the other hand, you can recover the geometric version if you take for phi the gauge of k squared divided by 2. Well, this is homogeneity. This is just a multiple that depends only on dimension times the volume, because this is just a homogeneous function. So, and you can observe that the Legendre transform of this function is the gauge of the polar square divided by 2. So, and of course for the Euclidean ball this is the same. So you recover, if you apply this, you recover the geometric. Okay, so there exist many proofs for this inequality, more modern proof, I want to say. In particular, there are Joseph Lehead gave 2 or 3 proofs of this inequality, but they all rely on some, in general, some geometric insight, right? It's not a somehow purely analytic proof. Of course, I should mention here the recent proof that was presented by Tom Courtade, and which proposes to analyze this inequality from the dual point of view of Talagrand, asymmetric Talagrand inequality. Okay, maybe I'll comment a bit more on that later. Okay, so what I would like, you see, in the geometric case, we saw that there is this process of Steiner symmetrization that increases, and I would like to have something that is a bit similar in the functional case. So what does it mean? So there are two typical things I would like to have. First one would be to have some kind of path that connects phi and phi star, okay, and that along this path I have some log-concavity or something like that, and this path passes at the middle through the fixed point x squared over 2. You can imagine that. So some form of duality in the level of path among all convex functions. And this is actually possible, but if you are, say, on Cn, if you have a complex structure, you can do something like that. Actually, it works. And this is connected to complex interpolation, or to homogeneous complex Mohr-Ampère equation, which in this context is the same. So this is very nice, but I don't know how to make it work in other without this complex structure, this complex Mohr-Ampère equation. So I think this is a very nice question. I would like, if you have some insight on this. It seems natural that there should be something from in this direction. And another possibility is more in the spirit of this Steiner symmetrization, is that you find a path that connects your log-concave function to your Gaussian, along which your volume product increases. Okay, so this was recently answered by Nakamura and Tsuji. So indeed, proved a remarkable result that the volume product increases when your log-concave function here evolves along the Fokker-Planck or heat semigroup. Okay, but in their paper, this is obtained as a byproduct. This is not proven directly. They work with some other functional that is related to the Laplace transform, and they obtain the result for the Legendre transform by a limit. Okay, so it was not a direct proof, and so somehow my goal today is to explain that indeed there is something to be understood that allows you to prove this somehow that directly. So to give it really this streamlined approach that we want. Okay, so I will now recall a few facts about this Gaussian semigroups. So I will denote PT the heat semigroup. So it's just convolution with this Gaussian with variance to T. So this solves the heat equation. So the problem with heat, we already saw it, is that of course it tends to diffuse. It does not preserve variance. So what you want to do somehow is rescale it slightly so that you really tend to a Gaussian. This is well known. So there is a rescaling. I think we saw it also in the talk by James. So this is the dual point of view here. So you can rescale in time and in space. And this is what's called the Fokker-Planck semigroup, and we solve this equation. So you have an extra first-order linear term. Okay, and the advantage of this, which again it's just a rescaling. The advantage is that now it connects F to a Gaussian. Okay, that has of course a weight because both PT and QT preserve the integral, of course. Okay, so this is a divergence, and so have this weight, but in this case it really tends to a Gaussian by the rescaling. Okay, so very useful observation is that these semigroups, either PT or QT, preserve log-concavity. Okay, so there are here several dates somehow. So let's try to guess what these dates are. The first one I'm not sure, but okay, in general this is the reference for this is a paper by Prekopa that says that let's say the more general result from which this observation follows.
Before there was the paper by 2 or 3 people in Soviet journal.
Exactly, 2 or 3 people. This is 2 or 3 people in Soviet journal. So ask. I learned this very recently, so I'm sorry I did not check the paper. I saw the title. The translation has something like preservation of log-concavity, so it seems pretty explicit. But I cannot tell you more about that. But it's the reference is in our paper. So this is Perkova, and this is the Blaschke-Santalo, because this was a very important step in understanding this, and I will try to give you very quickly the proof that is essentially inspired by the paper by Blaschke-Santalo. Okay, so how does it go? So first, the argument of Prekopa is, I think you all know it. It tells you that if you have a log-concave function, you integrate some of the variables, what you get remains log-concave in the other variables. Okay, and here you just apply this to F, to this product, and this is log-concave in X and Y, right? If F is log-concave. So this follows directly now. So I'll try to give you the proof. So what we will do, without just already T, so let me take T equals 1/2 because the notation is simpler. So I look at minus log p1 half of exponential minus phi. So here is the definition, minus log of exponential minus phi. Now this is just usual Gaussian kernel, standard one, and there is some constant, some normalization constant that, of course, will not be important here. So the question is, you want to prove that this capital phi is convex. This is the statement. If little phi here is convex, capital phi here is convex. This is the statement. So what you do, you fix, you prove convexity is a one-dimensional notion. You just fix one line, y0 plus s theta 0, and you want to prove that as a function of s, it is convex. So you just need to prove that the second derivative at 0 here is non-negative. Questions?
I mean, there could be some different, a little bit different explanation, because if T is a density of the sum of two log-concave random variables, one of them is Gaussian.
Yes.
The sum of two log-concave random vectors is log-concave. So
by what, Bobby?
by Prekapa.
Yes. I'm just proving this fact. You agree?
But in that case, you don't need to mention Gaussian.
Yes. I'm giving a particular, but I hope you will see that the argument works in the general case. But yeah, I agree, of course. So let's do that. So I recall here the definition. Let's do the computation. You take the derivative in s. So here you have in s. You have theta 0 scalar x minus y0 minus s theta 0. And then you have again this density, and you divide by this density. So it makes sense to give a name. You see, this is a probability here, density. So from now on, you see S, okay, no. So of course here, recall that y0 and theta 0 are fixed. So as a function of x, this is the probability density. So let me call mu 0, this is just at s equals 0. I took s equals 0 for the second derivative, so I'm calling this mu 0 because it will appear twice. And so let's compute one more derivative. So what happens here? When you take the derivative in here, what you get is just theta 0 square against this probability measure, so this gives you 1. And you have two other terms. You take the derivative here, it gives you another term of this form, theta 0x, and you have the derivative here, which is the square of what you had before. So if you really look at what is going on, you will get, actually it's the variance of this plus a constant, and I took out, the constant was theta 0, y0 that I took out. You really get the variance of this function x theta 0. This is as a function of x, right? So, believe me, maybe many of you have done this computation more than 100 times. I did at least. Okay, so this is the formula. And now the question is why is this non-negative? Right? So it turns out there is a beautiful result that we will use several times due to Blaschke and Lieb that tells you that if you have a convex function and you call, let me give this notation mu v, it's just a probability measure with potential v, so I just normalize. I hesitated to remove all normalization, but okay, I think I will keep them for now. Then you have that for any smooth function or locally Lipschitz function u, the variance with respect to this measure of u is dominated by the following quantity. So you take the Hessian of v, take the inverse, and it acts on the gradient u, and then you dot with gradient u. Okay, so this is the result by Blaschke and Lieb, which, so let's see in our case what it gives. If you remember, our function v was phi of x plus this Gaussian x minus y squared over 2, if I am not mistaken. Yeah, so this is our convex function here. And if you look at the Hessian of this, well, you have the Hessian of phi, which is non-negative, and here you will get the identity. So this Hessian is greater than the identity, So of course the inverse is smaller than the identity. So for this measure, I have this. This is a Poincaré inequality for my mu v. And now you apply it to the linear, we are applying it to linear functions. So linear functions, this is 1, because theta 0 was normalized to be 1. So this is 1, and this is the variance. So indeed, the variance of a linear function is smaller than 1, and this is exactly what I needed for the...
One can prove without Blaschke-Santalo, because this measure is log-concave with respect to standard Gaussian, therefore it is a Lipschitz transform.
Yes, but you are using a hammer, you're using Caffarelli. This is a very basic, actually, this, okay, you see, can you, okay, just last comment here, believe me, if you adapt this argument, you get Prekova. Of course, here that it's more complicated, you need to have some relation between the derivative in t and the derivative in space, but if you have global convexity, this is exactly what is giving you, that indeed the second derivative in time is above this quantity.
So, I mean, your conclusion is just this Poincaré inequality. That's
yeah.
the point. Yeah. I mean, it's just Zachary Henry.
Sorry?
Zachary Henry.
Yeah, but all this is much. It's after we all agree that it's all after Blaschke-Santalo.
Oh, okay.
76, and also I don't know if for
Emery did not use no Caffarelli, nothing.
No, but you use other things, right? So essentially, I will give you the proof of Blaschke-Santalo. So I don't know if there is a proof for Caffarelli in 3 lines. I don't think so, but there is a proof of Blaschke-Santalo in 3 lines. Okay, and it is essentially the gamma 2 that was used by Blaschke-Santalo. So except that this proof was anticipated in another setting, in the setting of complex. Well, it was used by Hermander, his argument for solving the d-bar equation. Okay, so here it goes. You introduce the natural Laplacian associated to your measure. Okay, so this is grad f, the adjoint in this L2 of mu space. So you have this, and now you just what you have to do is 2 integration by parts. It's Bochner formula, so that LF square, so L square FF. This is equal, so this is just the Hessian of V grad U. Sorry, here I missed LF is here it should be F. Okay, sorry. So Hessian V grad F plus and here you have the superfit norm of this Hessian, so the sum of all secondary units. Okay, and now what you do is that you drop this term and you keep only this term. Okay, and now this is just a dual formulation. Believe me, if you go through duality through this operator L, then this is just dual in sense of quadratic forms. If you go on top of this, so that's essentially the proof of the Blaschke-Santalo. Okay. No questions here. So a really very influential result. We'll see it again later in the talk. Okay, so now let's go back to our problem. We have the volume product here, and I want to prove that this is increasing in time. So what I do, I take exponential minus phi, and this is the function that evolves along my Fokker plan. So this will connect at t equals 0 exponential minus phi, and at infinity a Gaussian. So because I'm really really lazy, I prefer to work with the heat semi-group because there is one less term. And we saw that there is linear invariance in the volume product. So of course it's the same. The limit, okay, there is a self-scaling in this process that you don't see, but anyway, if you want to prove just that it is increasing, you can just use the heat semi-group, and this is what I will do now. Okay, so this pt of exponential minus f, by the result we saw, it's a log-concave function, and so I will call phi t the convex function. Okay, so phi t. Remember, so here maybe I should keep it. So if you want, this is the definition of phi t. So, okay, exponential. So this is phi t. So we know now by this result that it's convex. And let me call psi t the Legendre transform. I will try to be consistent with my notation. So the quantity we want to look at is pt of is exponential minus phi t times exponential minus psi t. Okay, and of course the heat semi-group preserves the integral, we said. So it's really about this quantity. It's really about the evolution of this quantity. So our goal is to prove that this quantity increases in time. Okay, so now we need to compute derivatives. So the evolution of phi t, this is very standard. I mean, I'm sure you already done this computation several times. Again, I think I did it more than 100 times. So if you look at phi t, the evolution is Laplacian phi minus grad phi square. Maybe sometimes called Jacobi-Bellman equation, I'm not sure. Okay, you just compute. So this is okay for phi t. Maybe you can prove maybe you can prove by a maximum principle here too that this preserves. I don't know, I haven't. So this equation preserves convexity. Now the question is really what happens for psi t. Okay, and I think for a long time, this idea, for a long time I could not believe that it would be possible to have a formula for psi t. Because you know there is a supremum and so on, so it's really not clear that you can, and so somehow the original work of Nakamura and Tsuji somehow give us hope that, okay, maybe there is something, we should really look at this quantity psi t and see what happens. So our main result is really a lemma or a fact. I had only theorems in my Beamer style, but this is the result. So the fact is the following. Here is just the same notation. So phi t is the evolution of pt of exponential minus phi, psi t the Legendre transform, and now our result is that psi t satisfies the evolution equation. As follows. So psi, the derivative in time of psi t at the point z is equal to z squared minus trace of the Hessian of psi t inverse. Okay.
In dimension 1 it is nuclear or not? The same.
Because you can use that f. You have the inverse. I don't know. Yeah. Maybe one step, I will give you the proof. I think one step is clear in dimension y.
Superlinearity condition is just so that the inverse makes sense.
Okay, yeah, you're right. So I was a bit sketchy here. I'm making some, so this is actually a very interesting point. So superlinearity, so here I am looking at integrals of functions that, you know, of course, I am interested only in things that are finite integrals. So of course, already phi, you know that it is, it tends to infinity at infinity. It's called, okay, I forgot it. So you know that phi tends to infinity at infinity. Here I'm asking, so it is above linear. And here I'm asking slightly more than, so yeah, you already know this is automatic, right? That you have something like this, because it's a convex function that tends to infinity. And here I'm asking slightly more. I'm asking that phi of x over norm of x tends to infinity. This is what I call it. So if you do that, you see that this guarantees that the Legendre transform has domain which is equal to Rn. The Legendre transform will define over all Rn. And this saves me some problem of what happens if it has a domain that depends on t that I need to differentiate. But formally, it should not be, okay. I've not tried to generalize really. There should be a way to deal with to remove this assumption. Of course, from the point of view of the inequality, you can always add a Gaussian or whatever, and you're fine, right? So it's not a restriction from the point of view of the inequality. It's more a restriction to have something nice. If you do that, then you know that phi t remains superlinear. Psi t will be smooth on all of Rn. It will also be superlinear, so it's really convenient.
Gradient of phi t and gradient of psi t are like inverses.
Yeah, this we will use it, of course, they are inverse. This is how originally the Legendre transform is defined, as the inverse of the gradient map. Okay, so I will give you the proof of this result. So the first observation, that's very general, it's not particular to the specific evolution, is that it's what happens when you perturb a convex function, what happens for the Legendre transform. So this is like a general fact that has nothing to do with this is the proof of this. Here I recall the definition of the Legendre transform, and so I'm working at a fixed point z0. Okay, and I want to understand the derivative at t0. So when I fix these two things, this supremum is attained, because of my assumption actually, at some unique point, which I denote x dot, x0 here, which satisfies this equation. Okay. Now, what I will do is just a Taylor expansion. This is how you compute derivatives. So you do the Taylor expansion. You want to understand psi t0 plus epsilon at point z0 fixed. So here I rewrote the definition. Here I have done nothing here except the point x, I call it x0 plus epsilon y. Generic point, it's a generic point in Rn. But of course, what is the idea here is that if epsilon is small, the point x where it is attained will be close to x0. So by writing this, you expect that indeed the y, you say, will remain at least bounded, so that this is indeed small. So you don't have to compute the supremum of all y's, but y's that remain bounded. This is what you hope. That's why you write it like that. Okay, so now let's do the Taylor expansion. You look at the first order. So the first order is you have z0 x0 minus phi t0 x0, and of course by our choice of x0, this is exactly psi t0 z0. So the first order is the first order. And now you look at the order in terms of epsilon. So what do you have is here epsilon z0y, and here you make the Taylor expansion. So here what you have is the term epsilon. So here I take derivative in time. So I have epsilon derivative in, well, I call it time, but it's just a parameter. Derivative with respect to the parameter t at x0. And the other first order term is here the derivative in space. So you have epsilon gradient phi t0 at the point x0, y. And here is where I'm cheating. I'm assuming that it's kind of uniform in y. And this is for this, if you have this assumption, for instance, superlinearity, it's okay. You will indeed, it's enough. This capital O is indeed uniform in y. Okay. And now you look at the terms, and you see what's happening. So this is the term we wanted. I take it out. Epsilon dt phi 0. Okay, this is what I wrote here, because x0, this is the observation that I will use several times. X0 is the gradient of the Legendre transform at z0. Okay, they are inverse one to the other. And the other term, what happened? Well, this was the definition. You see, you have z0y and gradient psi t0 x0y. Because of my choice, the other term vanish. So this is the only term that remains. Okay, so this is the proof of this first ingredient, which I believe appears implicitly or explicitly in many problems about convex optimization. Now, you just have to recall, the only thing you have to recall now is that there is an equation for phi t. Okay, that's here, so you can just replace, and find you what is phi, is what? You have Laplacian phi t at the point grad psi t, minus the gradient of phi t at the point gradient psi t. Okay, there was a minus, so now it comes like this. And of course, so this, what we said, the gradient of phi t is the inverse of the gradient of psi t, so here you get the z square. And now here, the Laplacian is the trace of the Hessian of phi t at this point, and again by the same property, the Hessian of phi t at the point grad psi t is the inverse of the Hessian of psi t. So it's very simple, extremely simple observation, but as we'll see, it's very, very useful. Okay, so here I'm back to my problem. I'm looking at the evolution along heat of my volume product. Here I recall what I have. So what I want to understand is that this is increasing. I will take the log because I've decided to normalize my quantities, but this is really, of course, not very important. So I want to prove that this increases, and so I compute the derivative. And I have, here it's just definition minus derivative in time of my quantity, and here this is what I will call mu of psi t, which is the log-concave measure with potential psi t. So here, now I use my formula. This, with the minus, it becomes that this is the trace of the Hessian of psi t, minus 1 minus y squared. Right? And you want to know if this is non-negative. Okay? And of course, now it's extremely tempting to go back to the Blaschke-Santalo inequality here for this first order derivative. So here I recall the definition. In the case of called psi t, my potential. So I wrote it in this form. Instead of writing variance, I said, okay, if u is centered with respect to my measure, then this is the variance. The integral of u squared is controlled by my quantity. Okay. Now, this is where I will use my assumption that phi was even. The fact that phi is even implies that along evolution it remains even, and the Legendre transform will also be even. So the linear, if you look at the linear functions, they are centered, right? So you can apply it to linear functions. So you have y, this is the coordinate y, yi squared smaller than the Hessian, and the gradient is just the, here is the usual autonomous basis associated. The autonomous basis ei. Now, if you sum over all ei, over all I, here you get y squared, and here you get the trace. So this Blaschke-Santalo gives you exactly what you wanted, that this derivative is non-negative. Okay, so this proves the theorem, and actually you see that it gives you a bit more. It gives you a bit more because it tells you that the Gaussians can be the only maximizers in the set. Again, I would like very much to remove this superlinear assumption, but at least in the set of superlinear, they are the only extremizers, and actually even the only local extremizers. Why is that? Why is that? Because if you have a local extremizer, since it increases along the heat flow, it means that at least for a short time, it must be constant. It's a local extremizer. So in particular, you have the derivative. So here I'm not taking the derivative at 0 because I'm not making any smoothness assumption at 0. But of course, as soon as you evolve, you're infinitely smooth. So I'm taking, say, the derivative at some time is 0. Now, it's easy to describe all equality cases in the Blaschke-Santalo inequality. They are spanned by the gradient psi against some vectors, spanned by the derivative of psi. Okay, so if you have to have equality, you must have all these linear functions to be in the space where there is equality. But these linear functions are linearly independent. So of course they have to span the space of these equality cases, which is at most dimension n here. So it means that actually these derivatives are linear combination of the yg of this linear function. This means that the Hessian of psi t is constant, and this means that psi t and therefore phi t is quadratic, and so this means that pt of exponential minus phi is a centered Gaussian. Now, it's easy to deduce from this that this must be a centered Gaussian. So either you use some sophisticated result that say that if x plus g is Gaussian, x must be Gaussian, but in this case it's just you can also use injectivity of the Fourier transform in L1. This implies directly. So this gives you this local. Okay, so now I would like to say a few words about the non-even case. So this is inspired by another work with Mathieu Fradelizi and Dylan Langharst. So in this paper, what we are doing is looking at the work of Nakamura and Tsuji on the Laplace transform. And in their work, they assume evenness, they assume symmetry, and we try to remove the symmetry. So to have a general statement for the Laplace transform without. And it turned out to be not as straightforward as one could think. It leads to interesting observations. But I don't want to introduce too much notation about the Laplace transform, so I will just adapt what we did in this particular case, which is the limit case, some limit case. I will try to explain why. So the first thing is that, okay, we say that there is a problem of the origin, and just having the zero inside the interior is not enough, because if the zero here approaches the origin, also the polar will increase more and more, and the volume will go to infinity. So you need some form of centering. So the simplest thing you can look at is to look at the infimum over all translation. Right? You take the infimum over translation, so the volume here does not change, but here this set changes. And indeed, it holds in this case that this is maximized by the Euclidean ball. Okay? This is actually, Meyer and Major proved that this quantity increases the time symmetrization. And you have the functional version, which is the analog of Kies-Ball result that was obtained by Arstein, Glartag, and Millman using this geometric result. Is that if you take the infimum over translation of the previously defined volume product, so here again it does not change, but here it has an effect on the Legendre transform, then this is maximized by Gaussian. And okay, so I really like very much Tom Coulthard's talk, and probably there is this issue about what is the centering and so on, but he almost convinced me that the point of view of using this symmetrized Talagant inequality at the dual formulation in terms of transport is probably nicer. I don't know. Okay, but this has some. Okay, of course, this geometric inequality is very important in the theory of convex bodies. No doubt about this. It makes sense to understand it also directly, probably. Okay. So I will give you the proof very quickly about the fact that indeed this so I do the same. Pt evolves along exponential minus Pt along the heat semigroup as before. So the first quantity here does not, sorry, this quantity does not change. So I want to understand the evolution of this quantity. So I take the infimum, I translate phi t, and I look at the Legendre transform. Now, see the difference now is that I have this infimum. So first thing is to rewrite this infimum because you see the action of translating phi means adding a linear term in the Legendre transform. So when you look at this exponential minus tau z phi t, what you really get is that you get an extra exponential here. Okay, this is a very basic idea, but it was used a lot in convex geometry, and I must say, in particular, in the works by Boas-Gartag, that this Laplace, the role of how a Laplace transform interacts with duality is very important. Okay, so here what I'm really looking at is the infimum of the Laplace transform of exponential minus psi t. You see, in the even case, this was just obtained at 0, so it was just the integral. But here, no. So I'm looking at the infimum of this Laplace transform. So here I recall definition. So now I will have two parameters, t and z, and this is the Laplace transform of phi t at z. And again, I put the log, but you can forget about the log, it's not important. So the important point is that I'm looking now at the Legendre transform of psi t, and I have this extra parameter z. Okay, and I want to understand the infimum over z of this qt, which is my log alpha that I want to prove increases. Okay, so what you can prove, which is what we prove for the Legendre transform, but if you pass to the limit, you get this. It's like a bit of a Hamilton-Jacobi inequality, in some sense, that the derivative in time of q plus the gradient in space of q squared is non-negative. Okay? So how you prove that? Well, the proof is essentially the same I gave you. You take the derivative. You take the derivative of this. So of course, the t is only here. So the derivative is again this trace of the Hessian of psi t minus 1 minus y squared. And now you see that the measure is not exactly the same measure as before because you have this this extra z dot y term for z fixed. Here z is fixed. Okay, I take the derivative in time, and I have just that. But of course, this remains log concave. I'm just adding a linear term, so this remains convex, right? Psi t here does not change the convexity here, the log concavity. So this is my new measure. So you see, I want to apply Blaschke-Santalo. Here it's not the Hessian of v, but of course, yes, it is, because this is the linear term. So of course, the Hessian of psi is the Hessian of v. So it's exactly the I can apply the Blaschke-Santalo. The only thing I am losing is the centering for the linear functions. So, well, I have to write variance, so I have an extra term that comes from the centering. And this extra term will be, will be the square of the, you see the square of the, when I apply to the linear function y, it will be the square of the integral of y with respect to this measure. But this is a now property of the Laplace transport. That this barycenter is the derivative in space of the Laplace transform. This is classical how derivatives of Laplace transform into barycenters. Okay, so you add up. This is so you have an extra term. This is square. You add them up, and you end up exactly with this formula. Okay. And now, why does this solve the problem? So now, this infimum, because again, you have some. This q is a convex function of z. So it's easy to see that it has a minimum and it's unique, has some uniform convexity. So the infimum of Q is attained at a unique point, which I denote ZT. So what I'm really looking at is QT ZT. And now I take the derivative in time of this. So I have the derivative in time at t is EQT plus, when I take the derivative here, I have the derivative of this flow ZT, whatever it is, I don't care, times the gradient at point, sorry, here is ZT, of my quantity. And I use my previous, so this is bigger than dt, and then I replace the dt q by minus gradient z at point t zt of this. Okay, but you see, because I am at the infimum in z, the gradient is 0. So this term is 0, and this term is also 0. And this gives you the proof. Okay, so my time is almost up, so let me say that, again, this argument, it's not exactly like this in our paper because we work with the Laplace transform, but I think the result by Nakamura and Tsuji about the Laplace transform is really of independent interest. It's not just that it gives you something for the volume product and for Santalo, but it's really something very interesting about the Laplace transform. And this is, I mentioned one of the result that we generalize. It's an inequality for the Laplace transform. So here again, L is the Laplace transform, and you want to look at some LP, LQ estimates. So here P is between 0 and 1. This is really the side that matters for convexity. So P is below 1, Q is negative, and you want to say that if F is in LP, LF is in LQ. So this amounts to some positivity improvement. This is a terminology that was used by Borel because, okay, now so Q is negative, so really you mean that LF is getting more positive than F in some sense. Okay, so you can prove inequality like this that Nakamura and Tsuji proved when F is even, and we kind of extend it to the case where F is general, either by saying that the result is true for any F if you take here the supremum over translation, or if you do the proper centering of fx to the power p. And this can be also rephrased in terms of reverse hypercontractivity. If you do some change of function and write things with respect to the Gaussian, it amounts to some reverse hypercontractivity when you go beyond the usual time that is given by reverse hypercontractivity, either by assuming some centering, you can go beyond the usual time. Okay, so my time is up. I will stop here. Thank you very much.